On this trip through the digestive system, we study motility, which is the action of muscles of the GI tract that mix and propel its contents from the mouth to the anus. Your goals for learning are to describe the type of motility found in each part of the GI tract, to associate each type of motility with its functions, to explain the control of motility in each part of the GI tract. Here's what you need to know. The anatomy of the larynx, the anatomical structure of unitary smooth muscle and how it is innervated, how the phenomenon of plasticity in smooth muscle affects its function. To see definitions of terms, click the bold red words. This is the first of 3 trips that we will make through the GI tract. On this trip, we will study motility and its control. The mouth receives food into the GI tract. Chewing tears and grinds food, reducing lumps to a size that can be swallowed. Chewing also mixes ingested food with saliva, moistening it enough to be easily swallowed. Click the mouth to observe chewing. Chewing is part voluntary and part reflex. The pattern and rhythm of chewing are set by the cortex and brainstem centers. Pressure of food in the mouth elicits reflex chewing actions. In summary, the type of motility in the mouth is chewing. The function of chewing is to mechanically break down food particles and mix the food with saliva. The esophagus serves no digestive or absorptive functions. It is simply a conduit between the pharynx and stomach. Motility in the esophagus is peristalsis, a progressive wave of muscle contractions. In the esophagus and throughout the GI tract, movement of the contents is accomplished by creating a pressure gradient as muscle contracts. Swallowing initiates primary peristalsis in the esophagus. Once begun, swallowing is a well-coordinated, stereotyped reflex controlled by the swallowing center in the brainstem. Click the esophagus to observe peristalsis. A bolus of food is separated from the contents in the mouth by placing the tip of the tongue against the hard palate. The soft palate rises to close the nasopharynx, preventing the contents of the mouth from entering the nasal passageways. As the tongue moves backward, the bolus is propelled into the oropharynx. Respiration is briefly inhibited, the larynx is elevated, and the glottis closes, which prevents food from entering the trachea. The epiglottis falls to cover the closed glottis. Muscles of the pharynx contract sequentially in peristaltic fashion. The bolus enters the esophagus. As primary peristalsis begins in the esophagus, the lower esophageal sphincter and proximal body of the stomach relax. The peristaltic wave is propagated by sequential activation of the muscles of the esophagus. As the bolus of food progresses, the larynx, tongue, and soft palate revert to their original positions and respiration resumes. The bolus enters the stomach and the lower esophageal sphincter closes, preventing regurgitation. Click the esophagus to see a swallow. Drag the slider bar to observe swallowing. When you have finished, click to continue. Drag the slider bar to observe swallowing. When you have finished, click to continue. The force generated by peristaltic contractions varies with the size of the bolus. Stimuli from the distension of the esophagus wall, relayed to the central nervous system, modify the pressure generated by the esophageal muscles. Larger boluses produce greater forces. A typical swallow propels a bolus of food through the esophagus to the stomach in about 9 seconds. Liquids travel more rapidly than solids in the upright human. Water travels down the esophagus to the lower esophageal sphincter in about 1 second. Water enters the stomach 5 to 8 seconds after the swallow, moved through the lower esophageal sphincter by the peristaltic wave. If a bolus of food does not progress all the way to the stomach, secondary peristalsis occurs. Click the esophagus to observe secondary peristalsis. When the esophagus is distended, afferent signals relayed to the central nervous system lead to a second wave of peristaltic contractions. Secondary peristalsis is common and is not felt by the subject. In summary, the type of motility in the esophagus is peristalsis. The function of esophageal peristalsis is to propel a bolus of food to the stomach. The stomach has several functions. It stores food, mixes food with gastric juice for digestion, and empties chyme into the duodenum. Different movements serve each function. The movements reflect the muscular structure of the stomach wall. Click the fundus to observe accommodation of a meal. Receptive relaxation occurs in the fundus and body of the stomach. Relaxation occurs with each swallow and permits the stomach to accommodate a volume of at least 1 liter with little increase in pressure. Peristaltic contractions mix stomach contents and empty chyme into the duodenum. Throughout the GI tract, the frequency of peristaltic contractions remains constant and is controlled by the interaction between pacemaker cells and smooth muscle cells. Each segment of the tract has a characteristic frequency. The frequency of gastric peristaltic contractions is 3 to 5 per minute. Click the body to observe peristalsis. Peristaltic waves begin mid-stomach, ripple over the body, and become stronger over the muscular antrum and pylorus. Antral contractions force chyme toward the duodenum and pulverize small lumps. Click the antrum to see gastric emptying. A small amount of chyme squirts through the constantly contracted pyloric sphincter with each powerful antral contraction. As the contraction progresses, it closes the sphincter completely, and most of the chyme is forced back into the stomach. This retropulsion effectively mixes food and gastric juice. Since frequency of peristaltic contractions is constant, the volume and contents of the stomach regulate the strength of contractions. In general, the greater the volume, the more rapidly the contents are emptied. The duodenum plays an equally important role in regulating gastric emptying. Fat, acid, and hypertonic solutions in the duodenum, as well as duodenal distension, slow gastric emptying. Fat is the most important stimulus for inhibiting gastric emptying. Fat is digested slowly, and the small intestine has to process it before additional chyme can enter. Acid must be neutralized to prevent damage to the intestinal wall and denaturation of digestive enzymes. Osmolarity must be slowly restored to normal before additional hypertonic chyme can enter. Distension inhibits gastric emptying until the excess duodenal volume can be handled by the small intestine. In summary, the stomach exhibits 2 types of motility: receptive relaxation that functions to accommodate a meal, and peristalsis that mixes and empties stomach contents. On this page, we will create a table that illustrates the regulation of gastric motility. Think about what you have learned about neural reflexes and GI hormones and answer each question as it appears. You must answer the question correctly to proceed. During the cephalic phase of control, stimuli like the thought, sight, smell, or taste of food elicit a response in the stomach. Will nerves or a hormone mediate the response? Will the neural response involve extrinsic nerves, a long reflex, or only the enteric nervous system, a short reflex? Will gastric motility increase or decrease as the stomach prepares to receive a meal? During the gastric phase of control, distension of the stomach elicits a response. Will nerves, a hormone, or both mediate the response? Which hormone mediates this response? Note that we use the term neural reflexes when the neural mechanism is not fully understood or when both long and short reflexes are involved. Will gastric motility increase or decrease as the stomach begins to work? During the intestinal phase of control, distension of the duodenum elicits a response. Will nerves or a hormone mediate the response? Will gastric motility increase or decrease as chyme fills the duodenum? Think about the function of the small intestine. During the intestinal phase of control, fat in the duodenum elicits a response. Will nerves or a hormone mediate the response? Think carefully about what the intestinal hormones do and what stimuli cause the release of each one. Which hormone mediates this response? Will gastric motility increase or decrease as fat appears in the duodenum? During the intestinal phase of control, acid in the duodenum elicits a response. Will nerves or a hormone mediate the response? If you chose hormone and thought it might be secretin, you were thinking about how the GI system works. Acid causes release of secretin. However, the reflex is so fast that the response is due to neural activity. Will the neural response involve extrinsic nerves or only the enteric nervous system? Will gastric motility increase or decrease as acid appears in the duodenum? During the intestinal phase of control, hypertonic solutions in the duodenum elicit a response. Will the response be carried out by nerves or a hormone? The mechanism for this reflex is currently unknown and may involve nerves or hormones that are not yet understood. Will gastric motility increase or decrease as a hypertonic solution appears in the duodenum? Intestinal feedback is collectively called the Enterogastric Reflex, named for its origin and site of action. This reflex is an integral component of the back-and-forth balancing act between stomach and small intestine as a meal is digested. The thought of food and presence of food in the GI tract regulate digestive activity. The autonomic nervous system can exert control over the operation. What will happen to digestive activity when the sympathetic nerves are activated? Sympathetic activation decreases digestive activities. The purpose of sympathetic action is to prepare the body for immediate physical action, such as fight or flight. Digestion can wait. What will happen to digestive activity when the parasympathetic nerves are activated? Gastric motility increases when the stomach prepares for and contains a meal. As the stomach empties, intestinal feedback adjusts gastric motility so that intestinal digestion and absorption are maximized. During digestion, segmentation is the primary form of motility in the small intestine. Segmenting contractions are stationary, oscillatory, alternating contractions, and relaxations. They mix chyme with intestinal juices and bring it into repeated contact with the absorptive epithelium. A single segment of intestine alternately contracts and relaxes, like these hands alternately contract. Click the hands to see contractions at the normal duodenal frequency. Intestinal segmentation is slow. The frequency varies. It is greatest in the duodenum, about 12 per minute, and least in the ileum, about 9 per minute. The frequency of segmentation is controlled by the interaction between pacemaker cells and smooth muscle cells. Click the duodenum to see segmental contractions. Let's color the contents of the small intestine to illustrate mixing. Notice how effectively segmentation mixes the contents of the gut. Because the frequency of segmenting contractions decreases from duodenum to ileum, there is a slow net movement of chyme along the small intestine. Small peristaltic waves that die out within a few centimeters also move chyme along. The slow passage of chyme through the small intestine permits maximum digestion and absorption of food. The volume and contents of the small intestine regulate the strength of segmenting contractions. Note that it is virtually impossible to exceed the absorptive capacity of the small intestine. Whatever you eat will be absorbed. Click the intestines for a summary. In summary, the type of motility in the small intestine during digestion is segmentation accompanied by limited peristalsis. Segmentation mixes the contents of the tract with intestinal secretions and brings chyme into contact with the absorptive epithelium. On this page, we will create a table that illustrates the regulation of motility in the small intestine during digestion. Think about what you have learned about neural reflexes and answer each question as it appears. You must answer the question correctly to proceed. When a meal is in the stomach and gastric motility increases, neural reflexes act on the ileum. Will the neural response involve extrinsic nerves, a long reflex, or only the enteric nervous system, a short reflex? Will activity of the ileum increase or decrease? During the gastric phase, a hormone also stimulates the activity in the ileum and relaxation of the ileocecal sphincter. Which hormone mediates this response? Since the stimuli for this reflex comes from the stomach, select the hormone produced in the stomach. This is called the gastroileal reflex. Like the enterogastric reflex, it is an example of the activity of one part of the GI tract influencing another. During the intestinal phase of control, distension of the small intestine elicits a response. Will nerves or a hormone mediate the response? Note that we use the term neural reflexes when the neural mechanism is not fully understood or when both long and short reflexes are involved. Will the strength of segmenting contractions increase or decrease as chyme fills the intestine? Think about the function of the small intestine. Remember that the volume and contents of a meal regulate digestive activity. The autonomic nervous system can exert control over intestinal motility. What will happen to segmentation when the sympathetic nerves are activated? Sympathetic activation depresses intestinal motility. What will happen to segmentation when the parasympathetic nerves are activated? After a meal is digested, segmenting contractions are replaced by migrating motility complexes, peristaltic waves that travel over successively more distal parts of the small intestine. Overnight, one may experience 6 to 8 of these complexes. Click the stomach to see an example. Strong progressive peristaltic waves begin in the body of the stomach and sweep over the pylorus. They empty the stomach completely because they relax the pyloric sphincter. This accounts for the forward progress of large objects, like a swallowed penny, through the GI tract. The next complex of peristaltic waves sweeps across the duodenum and first part of the jejunum. The next complex sweeps across the rest of the jejunum, and so on, until the waves reach the terminal ileum. The complex repeats from stomach to ileum about every 90 minutes during the interdigestive period. The intestinal hormone motilin mediates the activity. Click the intestine to observe the function. These powerful contractions perform a housekeeping function. They sweep undigested contents of the stomach and small intestine to the terminal ileum. Migrating motility complexes are a phenomenon of the enteric nervous system. Activity of extrinsic nerves is not required for the complexes, but it can modify them. Click the intestines for a summary. In summary, the type of motility in the small intestine during the interdigestive period is the migrating motility complex. It sweeps undigested contents of the stomach and small intestine into the terminal ileum. The major functions of the large intestine include storing and concentrating fecal matter. Chyme enters the large intestine as a result of the gastroileal reflex. Click the broom. Pressure in the terminal ileum opens the ileocecal sphincter. As the cecum fills, the sphincter closes, preventing the backward movement of chyme. Click the cecum. Typically, 500 milliliters of chyme enters the large intestine per day. Slow segmenting contractions, 1 to 5 per minute, knead the chyme and expose it to the epithelium so that water and salts can be absorbed. Contractions of the transverse and descending colon form haustra as contents are shuttled back and forth. Absorption of water and salts continues. Click the transverse colon. During a meal, propulsive multihaustral contractions and a type of peristalsis called a mass movement occur. A mass movement is a rapidly spreading intense contraction that leaves the muscle contracted for some time. Contents progressing out of the ascending colon elicit the mass movement that often begins in the transverse colon. Fecal matter is moved ahead of the contraction, filling the sigmoid colon and rectum by the end of a meal. Click the rectum. When the rectum is distended, a person perceives the urge to defecate. The rectum contracts, the internal anal sphincter relaxes, and tone in the external anal sphincter increases. Defecation can be postponed because relaxation of the external anal sphincter is voluntary. The rectum accommodates, the internal anal sphincter constricts, and the urge to defecate dissipates. Rectal contractions return the contents to the descending colon until the next mass movement. Click the sigmoid colon. When a person voluntarily relaxes the external anal sphincter, defecation occurs. Contraction of the rectum and sigmoid colon expel the feces. Voluntary movements that increase intra-abdominal pressure may aid defecation. Of the 500 milliliters of chyme that entered the large intestine, about 150 milliliters become feces. Feces contain primarily undigested foodstuffs and bacteria. Click the intestines for a summary. In summary, the type of motility in the large intestine during the interdigestive period is segmentation. This repetitive kneading movement promotes absorption of water and salts. During a meal, segmentation is replaced by a mass movement. These intense contractions propel the feces into the rectum, from which they may be evacuated. Reflexes regulate the activity of the colon. On this page, we will create a table that describes colonic reflexes. Think about what you have learned and answer each question as it appears. You must answer the question correctly to proceed. We have learned that increased gastric motility causes increased peristaltic activity in the terminal ileum. This is the gastroileal reflex that is mediated by extrinsic nerves and the hormone gastrin. In addition to stimulating the terminal ileum, the gastroileal reflex promotes propulsive contractions in the colon. What is this type of movement called? Segmenting contractions only move the contents of the colon back and forth. What is the stimulus for the defecation reflex? Do nerves or hormones mediate this response? Will the neural response involve extrinsic nerves, a long reflex, only the enteric nervous system, a short reflex, or both? Extrinsic nerves regulate defecation, and the enteric nervous system is involved in coordinating the actions of rectum and colon. During the defecation reflex, when the rectum contracts, which anal sphincter relaxes involuntarily? During the defecation reflex, when the external anal sphincter is voluntarily relaxed, will activity of the sigmoid colon increase or decrease? Peristalsis in the sigmoid colon causes evacuation. Pain, fear, and depression cause alterations in colonic motility. Frequently, the results are inhibition of motility and constipation. Anger, anxiety, and hostility may cause the opposite effect, rapid transit of contents. Physiologic responses to emotion vary from person to person, though none of us would deny that they occur. They are mediated by the extrinsic sympathetic and parasympathetic nerves to the colon. Vomiting is a complex reflex that is coordinated in the brainstem. It causes the forceful expulsion of intestinal and stomach contents through the mouth. Stimuli for the reflex include distension of the stomach, seasickness or dizziness from unequal vestibular stimulation, pain in the urogenital area, other painful injuries, increased intracranial pressure, tickling the back of the throat, noxious chemicals, toxins, or drugs. Click the figure. Vomiting begins with copious salivation and a deep inspiration.
Oh.
Click the stomach. Reverse peristalsis in the proximal quarter of the small intestine moves bile-stained intestinal contents into the stomach. The abdominal wall muscles and diaphragm contract, increasing intra-abdominal pressure. Click the small intestine. Strong antral contractions shift stomach contents upward through the relaxed lower esophageal sphincter. The soft palate rises to close the nasal passageways. The intestinal and stomach contents are forced up the esophagus through the upper esophageal sphincter and out the mouth. Click the stomach. Vomiting can serve as a protective reflex that expels harmful substances from the body. Excessive vomiting can lead to dehydration, electrolyte imbalances, and alterations in acid-base balance. Click the stomach to see the process again. Here's a summary of what we've covered. The motility of each part of the GI tract serves its functions and depends on whether a person is digesting a meal or is between meals. Reflexes that depend on the volume and contents of a meal control motility. Vomiting can protect the body from harm. To test your knowledge, click the quiz button to go to the self-quiz. To access cross-references for this topic in your Benjamin Cummings textbook, click here. To test your knowledge, click the quiz button to go to the self-quiz.